Welcome to Container-Based Architecture on AWS. We're Steffen Grunwald and Sascha Möllering, and we're both AWS solution architects. And today we'll cover the state of containerized application development and deployment trends. And this session will dive deep on new container capabilities that help customers deploying and running container-based workloads for web services and also for batches. So basically, the whole story started in 2014. In general, customers use Docker as a deployment model for their application because Docker images contain all dependencies like artifacts, libraries, and also configuration, which means Docker was basically used as a standardization of deployment models. For example, if you have different languages and platforms like, let's say, Java, Python, and Node.js, you have to implement different containers deployment methods depending on your specific target in your specific use case. With Docker, this is not necessary anymore. In general, it is easy to launch containers, easy to manage, easy to check the stats on a single host. But it becomes very challenging to scale to hundreds of containers because now you're suddenly managing a cluster, and cluster management is hard. So you need a way to intelligently place your containers on the instances that have the resources. And that means you need to know the state of everything in your system. So for example, what instances have available resources like memory and ports? How do I know if a container dies? And how do I hook into other resources like, let's say, elastic load balancing? And can I extend whatever system that I use, for instance, a continuous delivery pipeline, third-party schedulers, and so on? And also, do I need to operate another piece of software? And these are basically questions and challenges that our customers had, which led us to building Amazon ECS. And we have a large number of customers who are using Elastic Container Service to solve the problem. Amazon Elastic Container Service, or ECS, is a highly scalable, high-performance container orchestration service that supports Docker containers and allows you to easily run and scale containerized applications on AWS. Amazon ECS eliminates the need for you to install and operate your own container orchestration software, manage and scale a cluster of virtual machines, or schedule containers on those virtual machines. So with simple API calls, you can launch and stop Docker-enabled applications, query the complete state of your application, and access many familiar features such as IAM roles, security groups, load balancers, Amazon CloudWatch events, CloudFormation templates, and AWS CloudTrail logs. To ensure we can support every workload, we've provided containers running on Amazon ECS deep integration with the breadth of AWS platform features and capabilities to make it easier to run container-based applications in production. And these integrations include support for AWS VPC task networking, for instance, IAM roles and security groups for tasks, load balancer support, task autoscaling for clusters and tasks, and CloudWatch metrics and logs. We also provide a rich set of developer tools to make it easier to build complex applications on AWS, including integration with AWS Code Pipeline and the ECS CLI, which offers a simplified and powerful user experience for getting started with ECS. And with the ECS and autoscaling, customers can run applications that can grow to support cloud scale applications. This diagram shows the basic components of Elastic Container Service and how they work together. And I'll go through this environment and highlight each one and explain what it is. So to start off, we have a cluster of hosts running in Amazon EC2. And these are the actual compute instances where your containers run. On that machine, there's an ECS agent, and this agent controls what happens on that machine on your behalf. And if you want to run a container image on that host, you need to SSH in and execute the necessary commands, maybe Docker pull, Docker run, to get your containers up and running usually. In this particular case, the ECS agent will do that for you. So it runs the necessary commands on your behalf to launch a container, restart a container, fetch stats, and it will do it on your behalf without you needing to directly access the machine. At the top level, then there is the API, which is what you use to interact with the cluster as a whole. And you can give high-level commands to the API. For example, I can say I want to run 4 copies of this particular application distributed across 3 different availability zones, and I want to run them on any instance that's from the T2 family. It would take that command, check the state of the cluster that you provisioned, and find a way to place those tasks onto the instances to fulfill the command you provided. Because it is integrated with other AWS services, you can say that I want to run this task with this IAM role and run this task with another IAM role. So different containers have access to different resources in your AWS account. Then we have the task. The task is ultimately what gets placed on the instance when you ask it to run a container. The task is basically one step above the application container. The task is the application container and the configuration. So for instance, things like what environment variables are needed, does it need disk access, does it have a port that expects communication to happen on, or any specific CPU and memory specifications. Then we have the load balancer, and this is how you get traffic to your containers. So one example is one container that's running, and when the job has finished, it's exit and it's done. So more interesting, if you have a service you want to run persistently and it's receiving web traffic. With a load balancer, ECS will configure a load balancer on your behalf and place a task on instances in your cluster. When it places a task on your instance, it will also configure the load balancer to direct traffic to that particular task. This makes it easy for you to just give the command to the API and trust that traffic will reach the container without having to do any configuration or manual intervention to ensure that traffic gets there. And we also have ECS optimized Amazon Machine Image or AMIs. So those optimized AMIs are basically available for Linux and Windows, and you can bring your own images based on it. One typical example here is to use a tool like Packer to generate your own golden AMIs based on the ECS optimized AMI. And it expects the ECS cluster name in the user data. And you can also get SNS update notifications if those particular images are updated. Now let's take a look at automatic service scaling in ECS. Your Amazon ECS service can optionally be configured to use service autoscaling to adjust its desired count up or down in response to CloudWatch alarms. Amazon ECS publishes CloudWatch metrics with your service's average CPU and memory usage. And you can use these service utilization metrics to scale your service up to deal with high demand at peak times, and to scale your service down to reduce costs during periods of low utilization. Because scaling ECS services is much faster than scaling an ECS cluster, we recommend keeping the ECS cluster scaling alarm more responsive than the ECS service alarm. This ensures that you always have extra cluster capacity available during scaling events to accommodate instantious peak loads. Keep in mind that running this extra capacity, which could be, for instance, 10 to 15%, increases your costs. So find the balance between reserve cluster capacity and costs, which will vary from application to application. With IAM roles for Amazon ECS tasks, you can specify an IAM role that can be used by the containers in a task. Applications must sign their AWS API requests with AWS credentials, and this feature provides a strategy for managing credentials for your applications to use, similar to the way that Amazon EC2 instance profiles provide credentials to EC2 instances. And instead of creating and distributing your AWS credentials to the containers or using the EC2 instances profile, you can associate an IAM role with an ECS task definition or run task API operation. And the benefits are pretty obvious. So you have credentials isolation, which means a container can only retrieve credentials for the IAM role that is defined in the task definition to which it belongs. A container never has access to credentials that are intended for other containers that belong to a different task. And authorization, of course. Unauthorized containers cannot access IAM role credentials defined for other tasks. And also auditability. access and event logging is available through CloudTrail to ensure retrospective auditing. Task credentials have a context of task IAM that is attached to the session, so CloudTrail logs show which task is using which role. Let's talk about secrets management. Parameter Store is a feature of Amazon EC2 Systems Manager, and it provides a centralized encrypted store for sensitive information and has many advantages when combined with other capabilities of Systems Manager, such as Run Command and State Manager. Because Parameter Store is accessible using the Systems Manager API, the AWS CLI, and AWS SDKs, you can also use it as a generic secret management store. Secrets can be easily rotated and revoked. Parameter Store is also integrated with AWS KMS so that specific parameters can be encrypted at rest with a default or custom KMS key. Importing KMS keys enables you to use your own keys to encrypt sensitive data. Access to Parameter Store is enabled by IAM policies and supports resource level permissions for access. An IAM policy that grants permissions to specific parameters or a namespace that can be used to limit access to these parameters. CloudTrail logs, if enabled for the service, record any attempt to access a parameter. And if you want to run your containerized application in AWS, you need a Docker registry. Amazon Elastic Container Registry, or ECR, is a fully managed Docker container registry that makes it easy for developers to store, manage, and deploy Docker container images. And ECR stores your container images in Amazon S3, so your data is redundantly stored across multiple facilities and multiple devices in each facility. Let's spend a few minutes to talk about AWS Fargate. So with Fargate, you have no instances to manage. So no more patching of your operating system or your runtimes. And with the new Task native API, you don't need to worry about clusters. They are still there, but they are there as an organizational and security boundary. But you don't need to think about cluster utilization or auto-scaling of compute resources within the cluster. And with the resource-based pricing model, you only pay for the resources you provision for each task. So we think Fargate fundamentally changes how you think about consumption and how you will run and deploy your application with containers. Fargate is designed to be used with Amazon ECS, so the core API, scheduling, and placement concepts remain the same. And you continue to benefit from investments we've made over the past 3 years with access to the same rich set of features and capabilities to run in production and at scale without having to define and manage the cluster. The AWS Fargate support for Amazon EKS will be available in 2018. Shortly after reInvent 2017, a task definition repository was created on GitHub, which contains templates for common tasks. And this task definition repository contains examples for popular infrastructure components like Tomcat or Jetty, and feedback and pull requests are, as always, welcome. So let's take a closer look how a CI/CD chain can be implemented for ECS. In the first step, developers continually integrate their changes together into a main branch hosted within a source code repository system such as GitHub. In the second step, AWS Code Pipeline pulls the source code repository and triggers an execution of the continuous delivery pipeline when a new revision is found. Webhook support is available if the source is GitHub. In the third step, AWS Code Pipeline sends the new revision to AWS Code Build. Jenkins integration is also possible if you want, which builds a Docker container image from the source code. In step 4, AWS Code Build pushes the newly built Docker container image tagged with a build ID to an Amazon ECR repository. And in step 5, AWS Code Pipeline initiates the update of the AWS CloudFormation stack, which defines the Amazon ECS task definition and service. In step number 6, Amazon ECS fetches a new container from Amazon ECR and replaces the old tasks with a new one on the cluster. And in the last step, the new revision of the service is now running on the cluster using the specified launch type. AWS Fargate, or Amazon EC2. Let's take a closer look at how our customer MyTaxi is using Amazon ECS. MyTaxi is Europe's leading app for ordering taxis and was the first app of its kind worldwide when it was introduced in 2009. The app connects 10 million users with 45,000 taxis and allows them to book and pay for them in more than 40 cities in 6 countries, online or through the MyTaxi mobile app. Passengers also have the option to rate their drivers, making it possible for other users to find the best taxis and drivers. The app was originally launched by the startup Intelligent Apps, but since 2014 has been 100% owned by the multinational automotive group Daimler. MyTaxi designed a microservices architecture on AWS using Docker containers that is fast and scales easily to address extraordinary spikes in demand on days such as New Year's Eve. The entire infrastructure is built on AWS, where services such as Amazon EC2 and Amazon ECS support MyTaxi's Docker containers. And here we have a quote from one of the system engineers, Sebastian Herzberg, which is really interesting. In November 2015, we moved our Docker container architecture to Amazon ECS, and for the first time ever in December, we were able to celebrate a new year in which our system could handle the huge number of requests without any crashes or interruptions. So let's spend a few minutes to talk about Kubernetes. So the first thing we need to do, of course, is to introduce Kubernetes. Kubernetes has been around for a few years, but now it has absolutely taken the world by storm, especially over the past 12 to 18 months. It's also rapidly gained traction amongst AWS customers. So strip away the hype, and at its core, Kubernetes is an open source container management platform. And it's built to help you run your containers at scale and comes equipped with features and functions to build proper distributed applications using the 12-factor application pattern. And our customers told us, hey, running Kubernetes isn't trivial work, and we think we can better spend our cycles focusing on other applications. And if we had things our way, we wouldn't have to think about the nuances of Kubernetes deployments or configuration. We wouldn't have to worry about managing etcd or the masters. Amazon Elastic Container Service for Kubernetes, or Amazon EKS, is a managed service that makes it easy for you to run Kubernetes on AWS without needing to install and operate your own Kubernetes clusters. And with Amazon EKS, you get a highly available and secure Kubernetes control plane without needing to worry about provisioning upgrades or patching. One thing to start with, EKS is Kubernetes certified. This means you can use all existing plugins and tooling from the Kubernetes community. Any application running on any standard Kubernetes environment is fully compatible. This is a big deal for us and helps us to demonstrate our commitment to running open source Kubernetes. Those are basically the core tenets of EKS. EKS is a platform for enterprises to run production-grade workloads, and by production-grade workloads, we mean building applications at scale. EKS provides a native and upstream Kubernetes experience. So this means it is the same experience if you would install it on AWS yourself. EKS customers are not forced to use additional AWS services, but if they want to, the integrations are seamless and eliminate undifferentiated heavy lifting. The idea is that you're not forced to consume additional AWS services. The integration we will provide will be in an open source way. We want to commit them to the community. We give you the freedom to consume what you want depending on your specific use case. And last but not least, one thing I'm really excited about is that we will be very actively contributing to the Kubernetes project. And this is basically how Elastic Container Service for Kubernetes looks in your AWS console. So what you see here is configuration details like the API server endpoint, the Kubernetes version that is used, the subnets that you've used in your VPC, of course, the certificate authority to use this information in your kubectl configuration, and things also like the cluster area and the role area and the security groups that are used. So what are we building? What is the main problem that EKS solves? We wanted to build a set of APIs that allows you to easily provisioning a Kubernetes control plane, so you don't have to take care of certain problems like proper multi-AZ setup. You don't have to think about what are the best practices for deployment of Kubernetes. Things like, am I making sure that I'm sizing my master nodes in the right way? EKS has a managed control plane and can provide all these best practices. So the first problem we're solving is the managed control plane, which is pretty obvious, which means the master nodes and etcd, which is a distributed reliable key store. Worker nodes are handled like in the current ECS mode today. So you have to bring your own worker nodes and have to check them into the EKS cluster. You can think about EKS as a managed Kubernetes API endpoint, and it's upstream Kubernetes, so it's the same experience that you have today with Kubernetes in terms of what features are available, how do you interact with the cluster, which tooling you can use, but it's all abstracted behind this endpoint. So you can take your kubectl and communicate with the endpoint. So to highlight that, it's not forking, it's upstream Kubernetes. One of the solutions many developers and customers are using today is Jenkins, and we will take a closer look how our customer base is using Jenkins to deploy Docker containers in Kubernetes. When you start with Jenkins, essentially what you have is a Jenkins file, and with that you can very easily set up a pipeline. On the left you can see an example Jenkins file using YAML syntax, and all we're doing here is to define different stages. So in the first stage, which is a checkout stage, what it will do is that it will check out my repo if I've pushed a change. And in this repo, I have a Docker file. And with this Docker file, I can build my Docker container image. Now, I want to push the image I've built a few seconds ago to Amazon ECR. Of course, this could be also a different repository, like let's say Docker Hub. And in the last stage, to complete the deployment, we're using an Kubernetes native approach with kubectl to deploy the containers and the deployments and the pods in our Kubernetes cluster. This is one way we see our customers deploying applications. A different approach is, which is also a reference architecture, is to leverage the capabilities of AWS Code Pipeline. So a developer pushes a code change to a repo like GitHub or code commit, and Code Pipeline is constantly checking the repo for changes. And if that happens, you automatically invoke code build, and the service builds the artifact and the container and the Docker container image. So this image is pushed to ECR, and then it calls a Lambda function. And this Lambda function is basically a Golang function which uses the Kubernetes Golang SDK to trigger the deployment. So in the last approximately 30 minutes, we discussed several approaches to run your containerized workloads in AWS using Amazon ECS, EKS, Fargate, and ECR, and which CI/CD patterns a lot of customers are using today. And I hand over to Steffen, who will show you how to run your batch workloads using containers.
Thank you, Sascha. In the first part of this talk, we have seen architectures that help you to run container-based workloads. And most people, when they see containers, they think about web applications or online services. But for sure, there are also batch applications. And I want to point out in the remaining part of this session that containers and cloud services are actually a good fit for that. And I also want to point out some managed services that help you here to build the right architecture. But first, let's recap what is batch computing. Batch computing is running the same process over and over again with different data, or it is running the same process with the same data many times, but with slightly different parameters for each batch run. And the common batch characteristics are batches are done asynchronously during the night or at the end of the month or at the end of the year. And they run in very small batch windows compared to the time it took to collect and gather all the data that is necessary to be processed in this batch run. For example, you could process a month worth of data in just a few hours or a single day at the end of the month. Also, nobody of us, I think, wants to look at log entries written by thousands of batch jobs. And that's why you need a robust logging strategy and also a robust retry strategy to retry those jobs which failed and run as most jobs as possible during the night non-interactively. Also, batch processes are usually a chain of multiple jobs. It's not just a single job, but it's a chain of jobs orchestrated in fan out and fan in patterns and so on. So they need to be orchestrated. And usually there's more than one instance involved. Often there's tens or hundreds of instances which run your jobs. And the scheduler has to take care of matching the pending jobs to the existing free resources. And so this needs to be scheduled somehow. And for these characteristics, cloud is a great fit because of, for example, if you have embarrassingly parallel jobs, that means jobs which do not have any interdependency between each other, theoretically, you could process what a single instance can do in 100 days with 100 instances in just one day. The resource spending, of course, stays the same, but you get the result faster. You get the value of your job faster. Also, the container services as presented by Sascha and some services I will present in a minute have built-in scalability and reliability. So you don't need to take care of running an orchestration master over multiple availability zones in high availability mode. Also, it's all about your choice. So in the past, it was like you run your application, your online application during the day on some hardware. And to fully utilize the hardware, you used the remaining part of the day when there was no business hour or something. You used the same hardware to run the batch jobs, to fully utilize it. In the cloud, these are two different workloads and you can scale them independently. If you don't use your online service at night, fine, scale it down. And on the other hand, you can scale up the batch compute environment, and you can also independently pick the instance type. Maybe your job is CPU or memory bound or has high I/O requirements or even needs GPUs. You can pick the right instance type. And the same is true for storage. You could select instance types with instance storage. You can pick EBS volumes and tune the different EBS performance characteristics. Or you could even run your own shared file system in your jobs. And whatever your choice is, experiment with those settings. Try some different settings and check out what is the setting that helps me to get the job done as fast as possible and be as cost efficient as possible. And also in the cloud, you've got more than 125 services in AWS. And you can pick those to run these, to use these in your jobs. So no job is standalone. You always use some services, for example, to retrieve more data, to have more input data to process, or to store or collect the results. And depending on your usage patterns and commitments, you could select from multiple pricing models. Of course, you could use resources using the on-demand prices, getting EC2 instances, the on-demand price. Or if you can commit to 1 year or 3 years, you could use reserved instances that help you to get up to 60% discount of the on-demand price. Also for batch, there's scheduled RIs. Maybe you know the times during the week exactly when your job is run. And if you can predict that, scheduled RIs may be a good solution for you. Also, spot instance is, of course, a solution which helps you to run batch workloads. And I will come later to that. And even if you don't tweak the commercial stuff at day one, you only pay for what you use. And in case of EC2 and most Linux distributions, you are billed per second for your instance. Let's look at how a batch looks like in general. So without having any AWS services in mind. First, there's an event that triggers your jobs. That could be a change in your data. Many of the AWS services create such events. For example, if a file has been uploaded to an S3 bucket, you can send a trigger to a service. Or if a change is done in a relational database, such as Amazon Aurora, you can also fire a trigger here. Or if something is changed in your NoSQL database in Amazon DynamoDB, so you can listen to events and respond with a new job. Also, you can trigger events based on a schedule. With Amazon CloudWatch events, you get a cron-like function that helps you to trigger a job every hour or every night. And you could, of course, trigger the jobs on demand, maybe from your application on-premise or from other applications within AWS. Then the job with the job-specific parameters is stored durable in a queue that is scalable and highly available. And there the job with the parameters is waiting to be executed by a compute environment. So compute resources are executing your job's code with your parameters and are using downstream services to retrieve more input data or store and collect the results. And one thing that is especially important to leverage the pay-as-you-go pricing model is a component that monitors the queue depth, that looks at the job runtimes, that measures the current utilization and figures out when it's a good time to start more compute resources or get rid of some compute resources and release it to save money. And if you look at the ways how millions of active AWS customers implement batch workloads, you will probably see every kind of architecture because of the different contexts and the different requirements. But I want to point out three of them, or three important services that allow you to dump a big part of the operational workload to AWS and have more time for your application's logic. First, there's ECS, as presented by Sascha. It's easy to spin up workers in a managed cluster as tasks, and I will tell you in a minute how you can use ECS to implement batch workloads. And then there's AWS Batch, which introduces a slightly more opinionated design on top of ECS, adding lots of batch semantics and primitives that you usually need in batch workloads. And I know this track is about container-based workloads in AWS, and probably many of you are keen on solving a problem with containers, but I can't resist to highlight that AWS Lambda is actually a great idea for batch workloads, especially when they need high concurrency, very spiky and unpredictable load, and you can get rid, with AWS Lambda, you can get rid of the patching of operating system, either for the clusters or for the Docker image you use to implement your job. And there is no scheduling or scaling logic you need to take care of. So I urge you, if you hear batch, think about AWS Lambda first. And the recently introduced Amazon SQS as a built-in event source feature helps you with that by just putting your jobs as messages into SQS and process the jobs in Lambda. But this talk is not about Lambda, it's about containers. And containers are actually a great fit to implement your unit of work. If you pick the containers programming model, you have some features like images, for example. Images have well-established concepts for versioning and tagging and so on. So it's very easy to point to a certain version of your code to tell this job should be executed by this code. Also, images feature layered file systems, and this allows for easy distribution for new versions. If just the topmost layers are changed, that is very easy to distribute around many boxes. Also, you can pick the runtime and the programming language container, whatever fits the job. So there's almost no restrictions as long as it fits to the operating system. You can pick everything what is inside of the container. But when the job is being called by the orchestrator, it's just a black box, and it's very easy to integrate that in a chain of jobs. How could a batch workflow be implemented with ECS? Let's think about the following scenario. I would like to process an image as soon as it is uploaded by a user and scale it, add effects, or analyze the sentiment of the image. I could do that with ECS like that. You could put an image to S3 and define that the image should trigger, or new put of a file triggers an event that is put to an Amazon SQS queue. By means of CloudWatch metrics and alerts, you can define a scale in and scale out event based on the queue depth. Then ECS provisions clusters, so it adds more workers or reduces workers in the cluster, and each worker could have code that polls continuously the SQS queue and receives messages about the images or files to process. It loads the image, then processes it, and then copies the results back to S3. And a lot of icons in this diagram are managed by AWS, S3, SQS, CloudWatch, and ECS. And you've got full control over every component here in the wiring. And you also maintain the event loop in each container, in each worker. But there's still enough for you to do. So ECS is taking care to run the workers at the desired scale, but it's you who have to determine what is the right number of workers at runtime. And there's where AWS Batch comes into play. It introduces batch semantics for container workloads on ECS that are managed for you. And you can focus on your applications and the resources that are used by your applications, and AWS takes care of the rest. And that's what you need to take care of. First, you need to select an event that could be selecting an event in Amazon CloudWatch events. And you need to define your code as a Docker image that contains your logic and that calls downstream services that you need to provision, for example, to get more input during the batch job run or store the results. And the scaling logic, the queue, and the placement of the jobs in the computer environments, all is done for you. When we change the previous architecture with ECS to AWS Batch, it becomes slightly easier. Again, the example is as soon as an image is uploaded, you want to run your image processing and then put the result back to a bucket. In this case, with AWS Batch, you need to configure the bucket to fire a lambda function for each new object that is put. And this function takes the event data and uses the AWS Batch API to put a new job into the queue. And the AWS Batch scheduler looks at the job queue and figures out when, where, and how to run jobs that have been submitted, and approximately executes them in order in which they are submitted, as long as all dependencies on other jobs have been met. So a job can have dependencies on other jobs, and the scheduler takes even care of that. And this scheduler uses a job definition that describes mainly the image to run and the role that is assigned to each job, and some more configuration, which I will show you later here. Let's look at some example image, and I presented that Docker file for that case with the image manipulation. I use the manipulation here is flip an image. I used the Amazon Linux image as a basis, and I just install ImageMagick and the AWS CLI. So ImageMagick is very easy to use for conversion of images. That's why I will use that. And I will add a custom script, which I will also show you in a minute. And that script is also used as an entry point. So the semantics here is whenever this image is run and the parameters passed to this image as a Docker container, then this script gets the parameters and is executed. It's just a simple bash script. I get 3 parameters, that is the source bucket and the object in the source bucket and the target bucket. And then I've got 3 lines here doing my business logic. It's downloading the file from S3, then converting it by means of the convert command of ImageMagick, and afterwards copying the result back to the target bucket. And this is a usual bash script, so it can have return codes. And in case of an error here, this simple function is called, which I defined here. It emits an error message and exits with a non-zero return code, so that AWS batch knows that something went wrong. Overall, the script is pretty straightforward. It can focus on the business logic, and it does not need to have any AWS batch dependencies to run. So it could be run once or a million times a day, and it does not need to know about that is used. It's not called in the terminal, but in AWS batch. Let's talk about some batch concepts and the primitives that AWS batch has. That is definitions, the jobs, the job queue, and the compute environments. The job definitions are templates when a new job is run, and mainly it has it specifies, of course, the image and the role for the job at runtime to determine which are the AWS services it can call during the at runtime. It specifies resource requirements and also some other optional configurations. Most of this can be overwritten when job is submitted. A job is using this template. It uses the job definition. It can override the command or just add additional parameters. It can have dependencies on other jobs. So if you submit a job, you get an ID. If you submit another job, you can use this ID as a dependency. So you know that, so you make sure that the scheduler runs your jobs in order. And a typical job command could be as here in this JSON input. I used the source bucket and an image and then the target bucket. And I could override that in the job or already define that in the job definition. And be passed individually, one by one, using the API. And sometimes you like to run the same job only with different parameters. For example, to flip a list of images, or to run the same calculations many times with different parameters as part of risk calculations in financial services. And in this case, you can start an array job that allows you to run up to 10,000 jobs at once. And each job can access its index of that array and look up the concrete parameters for that index and use that in the business logic. And programs fail. And we've seen in the example, you simply use the established return code logic for this if something is failing. And there are some reasons for failure. Either the program fails, or there are connectivity problems, or spot instances is terminated, or some other unknown failure. And with many jobs submitted, so if you submit 10,000 per hour, you need a robust implementation of a retry strategy. And it's easy with AWS Batch because you can define the number of attempts in the job definition or the job, and Batch will automatically retry your job and also passing an environment variable to tell your business logic that this is currently a retry. Talking about compute environments, they come into 2 flavors, managed and unmanaged. With managed environments, AWS Batch takes care of the configuration and scaling. You could also define a lot of other choices like the pricing model, whether it is on demand or spot. You can also define the instance types or a mix of instance types if you like. With unmanaged environments, you gain even more control over every aspect of the provisioning and scaling of the ECS cluster. So you can do that on your own, and you could even run unmanaged compute environments on dedicated hosts. Whether managed or unmanaged environment, you could also bring your own AMI, and you could harden it your way. It could also allow you to mount volumes or provide specific drivers. AMIs just need to be based on Linux and need to be of hardware virtual machine virtualization type, so HVM images in short. And as AWS Batch places jobs as ECS tasks on the cluster instance, there is no need to install more than the ECS agent on your custom AMIs. And last but not least, there are job queues. These link jobs to concrete compute environments. You can have multiple job queues that have the same environment assigned. Job queues can have a priority. So the scheduler uses this priority to determine which jobs in which queue should be evaluated for execution first. So it's easy to implement something like a fast lane here. And job queues can also have multiple compute environments. For example, one that consists of spot instances and the other one consists of on-demand instances. And you define the order of the compute environments to define which one should get the job first. One remark about pricing. As I told you, we have a robust retry strategy, and that makes it a great fit for spot instances, so you can save up to 90% of the on-demand price. The scheduler is robust enough to cope with spot termination, and compute environments can be easily built from various types of instances and also mix spot and on-demand instances. It allows you to run the same amount of resources cheaper or to launch even more resources for the same money. Thus, it's either cheaper or faster, whatever fits to your workload requirements and characteristics. Start with spot, or at least start by mixing on-demand and spot compute environments to try spot once. And talking about pricing, there's no additional cost that incurs for the usage of ECS or of AWS Batch. You just pay for the resources that you consume, for example, the EC2 instances. I would like to show you how you can get started fast. So let's look at one CloudFormation blog post that it was written by Arya, a colleague of mine. And that one here is describing how you can use CloudFormation to create and manage AWS Batch resources. And it explains every type of resource that is spun up by CloudFormation and defines a job definition, job queue, and compute environments to start. Most important, there's a launch stack button which you can click to go to the AWS console and launch that stack. Just don't forget to change the region. This one here always starts in Ohio, but you could also switch to Frankfurt if you like. I launched that CloudFormation stack. It takes some minutes and the result can be seen here. And I want to show you how it looks like in the console. There's my job definition here. Just uses the plain Amazon Linux base image, and this one here has a simple entry point that's the bash, and it takes whatever is coming in as command and executes it. So this one here, this job will simply echo hello world. And we also got a job queue for that and a compute environment, which is currently at desired scale 0. Now I can run a new job. Say test, I pick the job definition I just shown. And now I run this job by submitting it. And on the dashboard, you can now see that this job has entered the runnable state and is waiting to be executed. And I got a compute environment which is currently set to 0 desired vCPUs, and because of a job being waiting for execution, this is now 2. And now the computer environment will be provisioned, and the job will finally be starting, running, and then succeed. And it looks like this here. I previously executed this. You see the job has been executed, and I can see the logs of the job here in CloudWatch logs. And you see Hello World here. Okay, so Sascha and me, we've shown you in the last 50 minutes how you can use EZ2 and EZS or EKS in combination with Fargate to run container-based workloads, and how you can use AWS Batch on top of EZS to run batch workloads. And depending on your need to control and tweak every little detail of the resources, you can save a lot of time by using the reliable managed services such as EKS or EZS or AWS Batch. I think a lot of you have great business ideas in mind for web or batch applications. Just go build, start with the managed services presented in this session, and you can focus on your idea and go live as soon as possible. And now, this is already the end of the talk. First, thanks for your attention and for listening. We're now happy to hear your ideas or get your feedback and get your questions regarding the services we've shown you or the architectures we've shown you. Just put your questions into the chat box, please, and we're happy to discuss them now.